Hello everyone. In this video we are going to talk about formulation of FEA for truss. Truss, as you know, is a member that carries loads and carries weights of other objects. And when you learn truss in statics, you learn that to simplify the calculations for a truss, we use the two-force member assumption, which means the forces in the members are along the members or along basically the line that is connecting the two endpoints. And this is valid when the weights of the members are negligible compared to external loads. The external loads are only applied at the joints, and we assume that the joints are only pins, simple pivots, simple rotary joints. Now, if some of these assumptions are invalid, can we still assume the two-force member? Well, if the weights of the members are not negligible, we can go ahead and break the weight into two equal parts and give each one of those halves to one of the joints of that member. That's how you can get rid of the weight. If the external load is applied on the member, not on the joints, then we can replace it by equivalent load on the joints. And the amount of load on the joints depend on where this load is applied on the object. Okay, so you can do a simple static analysis, right? So if you have a member like this and the force is not exactly applied in the middle, it's applied at 1/3 of the length from the left side, 2/3 from the right side, then if this force is F and you have two extra forces that you can apply, right? Assume that it's a static problem. These two forces that we need are going to be what? Are going to be related to these distances. So if this is, as I said, L/3 and 2L/3, you know, if you take a moment, so what you have is F times L/3 plus this reaction times the total what? Length, which is L, that should be equal to what? That should be equal to 0, or if you take about here, it's going to be 2LF/3 plus this reaction times L equals 0, right? So from there, you can see the ratios of those forces to F, correct? So one of them is going to be like the ratio of 3:1 to F. The other one is 3:2 or 2:3 to F, correct? So this guy is going to be what? This guy is going to be the bigger one. This guy is going to be what? This guy is going to be the smaller one. This guy is going to be the bigger one. So this guy is going to be like 2F/3, and this guy is going to be F/3. Now in this case, since you're replacing it, these forces should be downward to replace the actual F. So you replace them like this. Instead of upward, you make them downward. Okay, so you can break the force and use equivalent loads on the joints. What about the pins? If the members are not pinned together, if they are bolted or welded together or any other kind of fixed connection like rivets or something, can you still say that I can assume the two-force member? Well, you can show that as long as the the connecting lines of the centers of the members intersect at a common point. So if the center lines of the members connect at a common point, you can still treat your bolts or welds as smooth pins. So if you do some manipulations and some assumptions, you might still be able to what? Use the two-force member assumption, and this is very important because when we do FEA analysis for trusses, we use that important assumption that trusses are two-force members. If they are not two-force members, then we are dealing with beams or we are dealing with frames, which I'll discuss in my future videos. So right now, the only thing we have is two-force member, okay? And one of the good things about FEA, before I start, the FEA can not only give you the internal forces in the members, it can also give you what? Solve statically indeterminate trusses. So if there are more external forces and moments on the truss and you cannot solve for them, then by the methods in statics, FEA can solve for that. So here, if you have one end to be like cantilevered and the other end to be like pivoted, right? So you have a total of 5 reactions, which makes this statically indeterminate. The FEA should be able to calculate those reactions for you. So first we're going to see 2D or planar trusses, and then we're going to see 3D or space trusses, okay? So in general, as I showed you in one of my previous videos about the coordinate frames that we need in FEA for trusses, we need 2 frames for a truss. One is a fixed global frame that you use to keep track of the coordinates of the nodes, the orientation of the members, the applied forces and the boundary conditions for the truss, and the final solution nodal displacements. And this is a global fixed frame that you can put anywhere on the truss or even outside the truss. And then you need a local frame for each member. So you're going to have a bunch of these local frames. Each one is attached to each member. The origin of it is at one of the endpoints, at one of the nodes. And this is used to find the axial stresses and the strains and the forces in the members, okay? Because the force displacement relation can easily be described in this local frame. And you can see that in this figure, right? So here I have the capital X, capital Y global frame, and then for this member, I have the local frame, which is small x and small what, y. And as you can see, this frame is rotated so that the x-axis is along the member and y-axis is in the transverse direction or perpendicular to the member, okay? And the angle between them here is the angle of the member theta. Now, as I said, the origin of that, you put it on one of these nodes. So it's not like in here you have 2 of that. No. I'm just showing you this XY frame also on node J to show you that when you look at the nodal displacements, U's, right? If you show the nodal displacement by U's or UX and UY, you can either do it with what? U of that node in the big X, capital X and capital Y, or either show it with what? In the local direction. So again, the fact that I have 2 of these local and global frames, it doesn't mean I have 2 sets of them. I'm just showing the directions here for the reference. And similarly, the forces applied on the nodes can also be described either in the global frame or in the what? In the local frame. Now, of course, when we talk about the force displacement relations, what we need is this force here, the axial force, the force along the member. This is the one that is related to the displacement in the member, like the spring models that we used. So this is very important to us, this force, F small x. When we talk about nodal displacement, we can use either one, but typically we use the global coordinate and we use these displacements to basically draw the truss before and after the deformations. Okay, so if we want to show the truss before and after deformations, these global nodal displacements are more useful. But if we want to calculate stresses, we have to divide this force by the cross section of each member to get what? To get the stress. Or if we want the strain, we have to subtract basically which 2 U's, these U's. This U and this U, right? So U of JX small x minus U of I small x, and divided by what? By the original length of the member to get the strain, right? So each frame has its own application. Good. Now that we know about this, let's go ahead and find the global stiffness matrix for the truss, for any truss in general. We do it for each member and then we put them together to find the global for the whole truss. And the method of formulation here is the direct method. So for the trusses, the easiest way to do it is the direct method. Okay, we are not going to use minimum potential energy or residuals. The direct method is the easiest for a truss. So how do we do it? Well, in this case, the nodal displacement along the global axes and the local axes are related by a cosine and a sine of the member theta, right? So you can clearly see, if you look, that uix here is what? This u small ix cosine theta minus ui sine theta. And this is very easy to show, right? Because here I have this axis and I have this one, right? So this is u of I and y. This is u of I and x. And this guy here is u of I and capital X. And this angle is theta. So if you project this uix along the big uix, clearly the components of projection is going to be whatever it is times cosine of theta. But for this one, if you project this here, right, this angle is 90 degrees. So this guy here is 90 degrees minus theta. So it's going to be cosine of that, which is going to be sine theta, right? So there is a sine theta component here. There is a what? There is a cosine theta component. Of course, this is times uix, and this is times uiy. And see, they are in the different directions. This is positive, this is negative. So it's going to be like this, which is this formula here, right? And then similarly, you can find uiy from these two displacements. Just project them along this direction this time, which gives you this. So that is for node I, and then very similar or identical relation exists for the node at J, right? So if I want, I can relate now the U's in the capital system and the U's in the small system. I can relate them to each other by a simple transformation matrix, where the transformation comes from this rotation matrix 2 by 2, which is a rotation about the z-axis with angle theta, right, which comes from these components. If you see cosine, negative sine, sine, and what? Cosine. That's exactly what you see over here. That's for the node I, and a similar thing is for what? Node J. And since the displacements at node J has no relation to node I, and vice versa, the displacements of node I has no relation to node J, you get these blocks of 0. Okay? So here this capital U is all of these 4 guys. This is the capital U, and then all of these small u's, right? These guys, these 4 guys, they form the small u. Right? So I can relate the global and the local nodal displacement by a simple transformation matrix or a rotation matrix 4 by 4 like this. Good. Similarly, I can easily relate the nodal forces in the capital system and the nodal forces in the small, or the global and the local forces, by the very same what? By the very same basically T matrix, right? So they are related by the very same T matrix. By the way, if somewhere you need to find the inverse of this T matrix, for the inverse, all you need to do is these 2 by 2 blocks, you just transpose them. If you transpose these non-zero blocks, which basically means switching these 2 components, that's all you need to do. You get this one or vice versa. Okay, and that's because the transpose for a rotation matrix is equivalent to the inverse of the rotation matrix. Okay, the rotation matrices are orthonormal, so that's one of their properties. And you might say, where do I need this T inverse? Well, we'll see later when we go and solve the problem. The thing that we find is the capital U. But remember, if I want to find the strain and the stresses we need what kind of U's? We need the small ones. You see, these are the small U's, right? Because they are in the small system and they are in the local system. So if I find the big U's, I need to find the small U's so I can use them in stress and strain. And since big U is T times U, then U small is what? T inverse times capital U. So if I want local nodal displacement, I invert T and multiply by the global nodal displacements. And then I use them to find the strains and the stresses. So we need at some point T inverse, and you're going to see that in a minute. So far, we related what to what? We related global forces to local forces and global displacements to local displacements. Now, if I can relate the local forces and the local displacements also together somehow, that means I have a what? I have a full connection, right? That means now I can go from U to F or from F to U. Yes? Because here I can go from small u to what? To the big U. Here I can go from small f to big F. If I can go from small u to what? To F, or vice versa, I can go from F to U, because these relations are both ways, right? You can use T or T inverse, and I'll show you here, this relation, you can also invert it. Then that means I can also relate what? The capital U's and the capital F's together, and that's where we solve the problem. Because what? Because the boundary conditions on U's and the forces on F's, they are expressed in the global coordinates. So my loading and my boundary conditions are expressed in which frame? In the global frame. So once I relate capital F to capital U and I apply those conditions, I can find the rest of the unknowns. Okay, now the question is, how do I relate the small f to small u? Well, we know that since the members are two force members, the members are under pure tension or pure what? Compression, that we have seen in the past, right? And if a member is under pure tension or pure compression, then we know that the total elongation in the member is going to be what? We know it. It is F times what? L divided by A times E. Therefore, the K equivalent, which is the ratio of F over delta L, this is going to be A times E over L. So for each member, the product of cross-section and Young modulus divided by length of the member is the equivalent spring constant for that member, right? We know that one. And we also know that if you look at this member, as I said, this member is a two-force member like this. And what we have is, we have at the nodes, we have Fi and what? Fj, Fix, Fiy, Fix, Fjx, Fjy. But since the member is a two-force member and X is aligned the member, the only forces that we really have are the X forces. The Y forces do not exist. This force here and this force here, they do not exist. Why? Because the truss is a two-force member. Only the axial forces would exist, not traversal forces. If traversal forces would exist, then we call it a beam element, not a truss element. And we see that in one of the future videos. So here, the y's are literally zero, and you can see that here. Fiy is a bunch of zeros times everything, and Fjy is a bunch of zeros times everything. But what about the x's? Well, here, this is your two-force member, and this is Fi and small x, and this is Fj and small x. So this is node I, this is node J, right? And you say that this member is equivalent to spring. So instead of this, I can replace it by what? I can replace it by a spring, for which the constant is k, and then this node of it will move how much? Will move by u of j and x, and this node of it will move by u of I and x. Right? Correct? So if I want the magnitude of any of these two forces, all I need is to subtract the two displacements to get the total elongation and multiply it by k. So you see that Fix is equal to what? It is equal to basically k times Ux minus Ujx. Clean that. And Fjx equals k times Ujx minus Uix, which is, by the way, negative of Fix, and that's the condition for equilibrium. And those are written by these two rows. So I can now, if I put all of these small f's in a vector and call it small f, and all of the small u's in the small u, I can relate them by a matrix K, where matrix K is this guy here. You see? So now I have the relation. Now I can go from each one to another one. So I go from the small u to big U and small f to big F by a T. And then F here is what? K times U. So all I need is to plug in these three relations to go from small big F to big U, or vice versa. And that's what you see here. Right? That's all you see here. Because capital F is T times what? T times small f. So this guy should be small f. Now, is it really small f? Yes. Why? Because it's k times u, small u, and this guy is a small u, and I just showed you that the small u is what? I just wrote it for you somewhere here. That small u is T inverse times capital U. That's exactly what I have here. This is a small u, right? T inverse times capital U times f. That gives you, times k gives you f, and then T times f give you capital F, right? So that's what you see here. And if I plug in the T and the K from above, the total K, which we call it K of the element, the equivalent K of the element is going to be this matrix here. So this guy is equal to T, K, T inverse. This is this matrix here, which has geometry in it, which is angle theta, and it has K in it, and K has, again, what? Geometry in it, A and L, as well as the material, E. So A, L, E, and theta, they all appear in my stiffness matrix for the entire element. Good. This is the stiffness for any member, any 2D member with angle theta. And pay attention that angle theta is measured from which axis? From the x-axis to the right in a counterclockwise manner. Positive. We have to keep that in mind when we go and solve the problem right now. So hopefully it's all clear what we are doing. Now, let's solve a real example. So here I have this truss. The dimensions are given, the loads are given at this node and this node. You have two pivots here. Clearly, two pivots means this guy is statically indeterminate, because you have four reactions and there is no way you can find four reactions using three equilibrium conditions. So can we find these reactions? Can we find the displacement of each one of these nodes, and can we find the normal stress in the members? For simplicity here, we only calculated in member 5, in this member. Okay, but we can calculate it in any member once we have the nodal displacements. So we want to calculate everything: nodal displacement in global coordinates, the normal stresses in members, even the unknown reactions that you have over here and here. These four reactions, can we find them, right? So let's see how we handle this problem. So the first thing we do is, for each one of the members, we consider one element and two nodes. So we start giving numbers to the nodes: node 1, 2, node 3, node 4, and node 5. And these are elements 1, 2, 3, 4, 5, and 6. So 6 elements and 5 nodes. The order does not matter as long as you keep track of the 2 ending nodes for each element. You have to store them somewhere, right? So element 1, the ending nodes are 1 and 2. Element 2 is 2 and 3. Element 3 is 3 and 4. You have to keep track of that, right? If you want to write your own MATLAB code, or in ANSYS, the way it is used, or anything, it keeps track of the end nodes for each element. That's how, when you calculate the individual element matrices and you want to combine them into the giant matrix, which is for the whole truss, you know where each one of those components go into this big guy. Okay, if you don't know that information, there is no way you can put the truss stiffness matrix together. So what information do we need for each member? If you remember, I told you we need A for that member, we need E for the member, we need L for the member, we need theta for the member, right? You remember K was A, E over L, and then you also need theta. So for each member, you need to have these 4 pieces of info so it can form the element stiffness matrix. Now, do we have those? Well, in this case, the A for all of the members is 8 square inches, and the E for all of the members from a specific wood is 1.9 e to the 6 psi. So A and E are all constants for the members. The only things we need to calculate are L and theta. Now, for members 1, 3, and 6, these 3 members, 1, 3, and 6, the L's are all what? 3 feet. And the angles are all what? 0. So for these members, L is 3 feet and theta is what? 0 degrees. Since A and E are the same, that means the K for all of these 3 members are going to be the same, and this is the result. Now, the only thing different here is this guy here. This part I should really cross, because K1, 3, and 6, their magnitudes are all similar, but the nodes that they are connected are not like each other. Okay, so this part of it can be quite a bit misleading. The nodes, you want to write which node these elements are for. So this one here, the magnitudes are all right, but as I said, the nodes are not. If somebody says, which nodes are they? Well, look at them. K1 is between which 2 nodes? 1 and 2. So for K1, this part is right. The nodes that I have are what? Nodes 1 and 2. So U1 capital X, U1 capital Y, U2 capital X, and U2 capital Y. And the same thing for the columns. The columns are the same as the rows. So this part is only for what then? This part is only for K1. K1 is the same. But now, if I want to look at K3, for example, let me write K3 here. If I want K of member 3, it's going to be the exact same thing, 4.22 10 to the 5, and those numbers are 1, 0, negative 1, 0, negative 1, 0, 1, 0, 0, 0, 0, 0. But which nodes are on the side of member 3? You see the nodes are what? 3 and 4. So this is going to be U3X, U3Y, and then what? U for X, and U for Y, and the exact same thing goes to the rows. Yes, and if I want K of 6, it's going to be the exact same thing. Let's see if I can copy it so I save some time. And the only thing is it is going to be basically for which nodes? The nodes on the side of member 6, which you can see they are what? 4 and 5. So what you need to change is you have to basically change these guys to 4 and 5. And once you do that, then you are good to go. So let me just add them here for you. Okay, so that's K of 3, K of 6. They all have the same magnitude, 3, 6, and 1, but the nodes are different. Please pay attention to this part very carefully. Now, let's go to member what? Member 2. What's special about member 2? Well, member 2, if you look at it, that's this member. First of all, the length of it is 3, 3, so it's 3 square root 2, right? So L is 3 square root 2 feet. And what's the angle theta? Well, here, if we put the origin at the node that is at the bottom, right, then the angle here for this member is going to be this angle. So the angle is 135 degrees. Okay? And then here we go with member 4. Member 4 is the vertical member. And again, here the angle of this member is 90 degrees. And the length of it is the same 3 feet. And finally, we have member 5, where here the length is again 3 square root 2. And the angle is this time 45 degrees, right? That's this angle here. So this way you can find the K's for all individual members, K1 to K6. You found all of the K's. Now what you need is to put all of these K's together in the giant matrix and form the stiffness for the whole truss. Now what you need in this case is this big guy here is going to be what? As you can see from the dimensions, you have 4 elements here, and then you have 3 and 3. So this guy is 10 by 10. And why would you need 10 by 10? Because the rows are what? U1x, U1y, then U2x, U2y, U3x, U3y, U4x, U4y, U5x, and U5y. You have 5 nodes, each has 2 displacements, so this guy, and the same exact thing for the columns here, right? So this matrix is going to be 10 by 10, and how would you put these numbers in here? Let me explain that part as well. Once you learn this, the rest of it is done. So let's look at K1, right? K1, all the numbers are between node 1 and node 2. So remember here, this is U1x, this is U1y, and then U2x and U2y. So which area should this go? Well, the area is defined by U1x, 1y, 2x, and 2y, which if you look, it is going to be this area and this area, so it is going to be this 4 by 4 matrix. So that is exactly going to go there, and if you can see, that's the exact same thing. Right? So that's where that element 1 goes. What about, let's say, element 3? Element 3 is between what and what? Between, as you can see here, is between 3 and 4. So if I add them here, u3x, u3y, u4x, u4y, and let me just add the 5 as well here. So it's between 3 and 4. So 3 and 4 is here, and then it is here. So it's exactly gonna go what? It's exactly gonna go like this. So this is exactly where this K3 is gonna come, and this is exactly where this K1 is gonna come. Yes, now what about K6? It goes to 4 and 5, and 4 and 5 is here and here. So 4 and 5 has overlap with the previous one, so it's going to be this area. So the question is, what happens to these 4 elements that have overlap? Well, it's simply going to be summation of the numbers coming from those individual matrices. You add them together. So if there is any overlap area, you simply what? You simply basically add those areas together. So you see 1, 3, and 6 are not super bad, right? Now what about 2, 4, and 5? And 2 is not bad. 4 and 5 we need to pay attention to. Let me show you 2. 2 is between what and what? Between those 2 and 3. And 2 and 3, again, that's this area here, and then that's this area. So 2 and 3 is going to be like this. Again, you have areas of overlap, right? You have areas of overlap, but that's okay. You add the numbers together. Now, the interesting part is this elements 4 and 5, where the nodes are not adjacent necessarily. I mean, they are adjacent, but they are not in the matrix adjacent. In the matrix, the order is going from 2 to 3 to 4, not jumping from 2 to 4. And you can see here, you're jumping from 2 to 4. So how would you plug the numbers? That is the interesting part. So let me show you this part. So if I write these here, u2x, u2y, and u4x and u4y. If I look at this portion of it, this is only between 2 and 2, right? u2x, u2y, and u2x, u2y. So that goes where? That goes exactly between 2, 2, 2, 2. So it's going to come here. Let me clean this rest so we can see better. Let me just show you element 2. So that portion in the blue goes there because that's exactly in front of 2 and 2. Similarly, this area here, let me use a different color. This guy is between 4 and 4, so that goes to 4 and 4. So this is 4, and that is 4, so it goes here. What about these 2 other areas? For example, this here, this guy. Well, this one is between what? It's under column 2, row 4. So you go to row 4, but column 2, so it goes here. And finally, this area, which is under what? Under column 2, row 4, so it comes where? It comes here. So you see, you break that 4 by 4 into 4 2 by 2s, and they go onto what? Onto this kind of symmetric area, but they are split in the matrix. So that's how you put this element 4 together. Yes? And finally, if I want to show you 5, it's going to be very similar. Let me show you that as well. So here, what you need is 2 and 5. So u2x, u2y, u5x, u5y. And again, if I want to go similar, so we have this green area, which is under column 2 and row 2. So it goes again here. We have this area, which is 5 and 5. So it comes right here. And then we have this area here. And this is exactly the cross section of these two. So it should be here. And finally, you have this black area, which is on this other cross section of these, right? And that's this area here. Good. So this is where you split them and add anything that is over there. You add all the numbers from all matrices in the overlapped areas, and you get the giant what stiffness matrix for the whole truss. Good. Now this whole K times all of these unknowns, this whole K times all of these unknowns is equal to what? Is equal to the forces, of course, right? So let me move this a little bit off, right? So that K times the unknown of U equals this vector here, which are all of the external forces and the reactions. So now let's go ahead and look at our nodes and see what we have. So if you remember on nodes, nodes 1 and 3, we have these x's and y's that we don't know. So we can give them some name. So I would call them basically R of 1x and 1y. And then R of 3x and R of 3y. These I need to find. Node 2 is free, so it's all 0. So let's go ahead and write them. R1x, R1y. Node 2 has no x and no y. 3 has 2 unknowns. What do I have at node 4? X, there is nothing. Y is negative 500. And similar for node 5, again 0 and negative 500. So this is my what? This is my K equivalent times U equals F, right? That's this guy here that I wrote for you. Now, how many unknowns do we have here? This is clearly 10 equations, right? I have 10 equations. How many unknowns? Let's just mark them. So this is 1, this is 2, this is 3, this is 4. And do I have all of these 10 U's as unknowns? The answer is no. Here is where the boundary conditions are applied. What are the boundary conditions? Well, node 1 and node 3 cannot move in either direction because you have pivot at them. So U1x, U1y, U3x, U3y, all of these guys are 0. That's where the boundary condition is applied. And I have also mentioned it for you here. So really, I have 10 equations and 10 unknowns, 6 U's and 4 reactions. And I should be able to solve that because the system is linear. But the way I solve it is this. This is what I do. I get rid of the elements U1x, U1y, U3x, U3y, and the right-hand side. So the only equations I would focus on are the equations coming from what? Coming from the 3rd row and the 4th row, as well as what? As well as the 7th row, 8th row, 9th row, and 10th row. These equations where U1x, 1y, 3x, and 3y are set to 0, which basically means get rid of the 1st and the 2nd column in them, as well as what? The 3rd column and the 4th column in them. because they are multiplied by these zero entities. The rest of it is going to be exactly what you can see down here. Times the unknown u's is the known right-hand side. From here, it's a 6 by 6 set of equations unknowns. I can find all 6 u's. Right? And if you do that, these are the u's that you'll find. And then I can plug them back and I get my unknown reactions, or I can say that K times U minus F is the unknown reactions, and from there I can find my reactions to be like this. These two and these two. So not only I could solve for all nodal displacement, guess what? I could find all of the reactions. Remember, this problem was statically indeterminate. There was no way I can find for Rx, R1x, 1y, 3x, and 3y. There were 4 unknowns. But now look, I can. It tells me that Ry1 is 0, R1x is 1500, R3x is negative 1500, and R3y is 1000. And you can always check whether it makes sense or not. These two horizontal forces would cancel each other. This 1000 upward would cancel those two 500s downward. So the system is absolutely in what? In static equilibrium. If these numbers do not make sense after you solve, you do a sanity check, then there is something somewhere that you did not do right. So just do not trust your results because you solved for it. Check. See if the equilibrium still is valid, whether these numbers make any sense or not. So here, this one would tell me what? Would tell me that this is the truss in the beginning, right? That's the shape of the truss. Now, what happened to the shape of the truss? Node 1 and node 3 didn't move. Of course, they should not because they are pinned down, right? Remember, this is 1, this is 3, this is 2, and this is 4 and 5. What happened to node 2? Both negative components. So node 2 from here should go to the left and downward. So this is the new node 2. I call it 2 prime. And then what? And the x of it is more than y. So if you really want to do it, do a good job, right? Because you see the x component is, or y, sorry, the y is bigger than x. So it is something like this. And here I'm doing it with an exaggeration. If you look at node 4 is what? It's a small positive x and a lot bigger negative y. So 4 goes a little bit to the right and downward. So 4, let's say it comes here. And then 5, similarly, right? A little bit small x and a big negative y, so it should come here. So if you want to redraw the truss would look something like this. This is the deformed truss in red. And again, this is done with a lot of exaggeration, okay? And does that make sense? Well, of course. With the pin down of 1 and 3 and with these forces pushing down, of course, the truss would go down. So if you see this displacement don't make sense physically when you draw the transformed truss, right, or the deformed truss, know that something is somewhere wrong, okay? Always do a sanity check. So now that I have nodal displacement, now that I have the external reactions and everything, can I find, let's say, the stress in one of the members or any of the members? Yes. How? The first thing I do, now that I have the global displacements for any member, I multiply them by T inverse for that member to get the local displacements for the nodes of that member. So here I'm interested in member 5, and member 5 is between nodes 2 and 5. So the entries that I would pick are U2x and y and U5x and y. I pick those, which you can see these are these numbers, right, coming from these two and these two. They are coming here. I multiply the T inverse for that member. Remember, the angle of that member was 45 degrees. So this is T inverse with 45 degrees. And I get the small u's. And remember, once I have the forces, right, I can easily go ahead and what? I can go ahead and calculate the forces in the member or the strain or stress. How? Well, here are the axial displacements of the two end nodes. If I subtract them, it would give me the elongation of the member divided by the initial length, that's a strain, multiplied by E, that's a stress. And that's what you can see here. So the stress is E times delta local U over L. So the stress in this member is 87 Pascal, and F is simply sigma times A. So I multiply that by the cross section and I get 690 what? 6 pound forces. And I can do a similar thing for any other member. I just need to plug in the capital U's for them to get the small U's and to get the stress, the strain, the force in each one of the members. So this is a full truss analysis using the direct composition method or the direct formulation method for 2D trusses. For a 3D truss, everything is exactly the same, except you have now two nodes, but each node has 3 displacements, right? So node J has what? Has uj what? X, has ujy, and it has ujz. And exact same thing happens for what? Happens for the node I, right? You have these displacements. So you have 6 nodal displacements. Therefore, your K matrix for each element, instead of being a 4x4, it is going to be a 6x6. And when you have a 3D line, right, a spatial line in general, it's not determined by one angle, theta, like this. It is going to be determined by 3 angles, right? Theta x, theta y, and theta what? Z. You have 3 angles for any vector in the space. We call them theta x, theta y, and theta z, which you can easily find by what? Dividing the delta x, delta y, and delta z of the 2 end nodes by the total length. And these guys, by the way, you know their names in statics. We call them what? We call them the direction cosines of the member. And you know that they are not all independent. So cosine squared of theta x plus cosine squared of theta y plus cosine squared of theta z equals 1. So you only need 2 of them. You can get the third one always. And this K is still the same thing. This is still A times E over L for the whole member. And L comes from basically squaring these numerators, adding them together, and taking the square root, right? So we know the formula for L. K is the same, right? Except for, as I said, 6x6. And this K is the same formula that you had last time, right? It's what? It's T times the stiffness K times T inverse. So this is equivalent to this one, but again, instead of 4x4, it's 6x6. So now if you have a special truss, a special or 3D truss, you basically will be dealing with a lot more equations and a lot more unknowns, but the way that you formulate it is exactly the same as 2D. There is no difference here. Okay? So hopefully this lecture on truss analysis is useful to you, and you learned how to do the finite element analysis on a truss. I will see you in my next lecture. Thank you.